humanity. Your very existence is wrapped up in the things you are here to fulfill. Whatever you choose for a career path, remember the struggles along the way are only meant to shape you for your purpose.
Welcome to In Bloom. I am your host, Michaela Richmond, and this is a pro-humanity podcast.
Welcome to the In Bloom podcast. Today I have on James Ellias. I'm very excited for this episode. So James is a college physics professor. He has his own YouTube channel and he's working on a new theory of induction, which is basically a way of proving things from observation. It's like the scientific method. So we're super excited to get into all of this, induction, physics, etc. Welcome to the podcast.
Thanks, Ella. It's I'm actually really excited to be on this podcast because I've seen all of your guests before. Steve Patterson, a few other people who everyone has their own unique perspectives on how to live well and how to think about things. And I'm honored to be a part of that list.
Thank you. Okay,
Yeah.
So first, who are you? How did you get into physics? Give us a little bit of a background on James.
Okay, who is James? So let's see. I always was interested in understanding the world. When I was 12, I watched the movie The Matrix, which is kind of a funny introduction to philosophy, but that really got me. That was a huge moment for me watching The Matrix because it made me question a lot of things I had just never thought about before. Like, what's the nature of reality? How do I know I even know reality? It also raised moral issues, and these were immediately issues I was interested in. Then when I was 16, I took geometry class. And if you remember, if you had a good geometry class, you would have learned proofs. They would have given you a few basic assumptions that you're supposed to reason from. And then once you reason from those assumptions, you get more knowledge, you get some theorems, and then you can use those basic assumptions and those theorems to reason further to discover even more theorems. And the more theorems you have, the more power you have for measuring things in geometry, and the more power you have for discovering more things in geometry. And this fascinated me because I was introduced to what the correct method of reasoning was. And I made a lot of faulty assumptions about what the correct method of reasoning was from geometry. Geometry does not teach us everything about the right method of reasoning. And so I went too far with it in a certain sense, but it still was a formative experience for me. Then the next formative experience was objectivism. When I was 20, I learned about the philosophy of objectivism. Oh, I'm skipping a step. When I was 17, I wrote my own philosophy. I wrote my own world. Like I started and I wrote my philosophy like a geometry book. I started with a few assumptions. My three assumptions were: the senses give us data about reality, we have free will, and God exists. Those were my assumptions. And I deduced conclusions from these assumptions, like how we know things, what the nature of morality is. I deduced these things. And this philosophy was completely wrong, which I found out when I was 20, when I read Ayn Rand. Pretty quickly became an objectivist, although not that quickly. It took about a year for me to be convinced of a lot of different things. One of the biggest things was atheism. And the biggest thing that convinced me of atheism was that it was possible to have values without God. And so that was a big thing for me, which I know is also a big thing for you. So that's something maybe we'll discuss if you're interested. And then when I studied physics in college because that was the close, even though I wrote a philosophy, I didn't know philosophy was something you could really study when I was in college. And so I basically said, I want the most fundamental principles of existence. So physics is where I should focus my efforts. But unfortunately, I didn't feel like I was doing that well in physics classes. And I was getting B's, as you know, and I was getting B's at USC. Like USC is a good school, so I was doing okay. But the reason I was so dissatisfied is that, you know, from an early age, I really believed that before I accept something, I have to understand the proof. I have to understand the proof for myself. That's what it means to be a scientist. And in physics classes, I wasn't given the proof. We were essentially told dogmas, and then the closest we ever got to proving it was to use exercises to make a lot of deductions from these dogmas. So in other words, physics problems. You learn Newton's 3 laws, for example, then you make deductions from those. You find out where the projectile lands when it's launched, where the planet moves as it goes around the sun, all of these things. And you get two versions of a poor man's proof, which is you can see that all of the consequences are consistent. You can see that it logically makes sense. All of this forms a coherent system that doesn't lead to any contradictions or crazy things. The other thing is that you are, if you ever go into the lab, you can see sometimes that the predictions come true when you actually observe them. A lot of times, though, you don't have enough time to do the lab experiment properly, and then you do it wrong, and then you do it wrong. You don't get what's predicted, and then as a result, you're kind of left thinking, well, is the principle wrong, or did I screw up? I probably screwed up, but I probably screwed up because I find it unlikely that I'm like discovering some way that science was done wrong over the course of this simple thing. But I really don't know. It didn't give me any clarity on any of this. It was just a very dissatisfying experience. And from there, I decided to study physics on my own, which is something we could get into, I think, with other questions. But that's a summary. That's how I got into studying physics and philosophy.
That's amazing.
What I do now.
Okay, so I have a couple of questions. The first is first just an example, and you can tell me if I get this wrong, but the way that I understand how you went through understanding physics through proofs. It was basically the exact same experience that I had whenever I was trying to learn anatomy and physiology or biology. It was, I was put into a classroom and I was told, this is what you need to learn. This is truth. And my brain, because I think I'm very philosophical, like I always question why. And if I don't have a satisfactory why, like it doesn't make sense to me to tell myself that it is true. And so I'd always had a problem studying biology and studying anatomy because I didn't have the history that told me why it was true. Like, what are the experiments that these people went through to understand this is truth? And like you were saying, you know, we would do experiments in the classroom, and if I got something wrong, it was my fault because obviously this was true. Like, how would it be that, you know, I, out of all of the people that have ever done this experiment, am doing it, and finally finding this one contradictory point or whatever. So it's kind of like faith, right? Like you learn science through faith, even though science is supposed to be fact. And I think that's very, very fascinating. Whenever you were first talking about this, I was kind of caught off guard. And then I listened to your YouTube video and I was like, wow, this makes so much sense. And we'll get into this in a little while, the way that you go through things. But a question that I have is like, why did you continue learning physics? Because a lot of people, if they're bad at things or if they're not doing well, they just stop. And I think it's really interesting that you continued. You were like, I want to learn physics and I'm going to figure out how to learn this in the right way.
That's I didn't think you'd take us in that direction. That's a very unexpected direction to take this. Why? Well, I actually did take a break from physics for a while. When I got a master's degree in physics. I started going to grad school, and that's when I actually discovered Leonard Peikoff's method of induction. Leonard Peikoff is an objectivist philosopher who used Ayn Rand's ideas to produce his own theory of induction. And a lot of my ideas, and I agree with about half of that theory of induction, is the way I'd say it. But that half was incredible. It completely boosted my ability to actually understand physics. And that got me through grad school. But still, I did get fed up because at the time, I didn't know that it was being, I actually didn't even really know that it was being taught in a way that wasn't conducive to a real scientific method. I thought I was just not that good at it, basically. I did conclude I'm just not that good at this, basically. And I only slowly learned that what was slowing me down was my virtues, not my deficiencies. I actually was slowed down because I wouldn't accept something till I saw the proof. And so I was constantly just stopping and unable to do the exercises. I was also doing some things kind of wrong psychologically. Like I was hesitant to ever admit that I wasn't getting it. And so I would just keep hitting my head against a problem without asking for help. Although a lot of times I would ask for help and then that didn't help. But anyway, because the professor wasn't explaining in terms of the proof anyway, he wasn't addressing what I needed anyway. So, I'm not sure what I could have done differently. But anyway, so I took a break. I ended up working at the patent office as a patent examiner. And you may have heard of someone else who worked for the patent office before he was famous. This is a joke I always tell. Albert Einstein worked for the patent office of Austria before he came up with his theory of special relativity.
Interesting.
So I always tell this joke. Yeah. So I did, but basically to answer your question, the reason I came back to it after only 1 year at the patent office is I just couldn't stop thinking about fundamental issues. I couldn't stop thinking about philosophy. I couldn't stop thinking. And eventually for a time, I did swear off of physics because I was so fed up with it, but I never stopped thinking about philosophy. And that eventually, after I quit the patent office, I started tutoring and started being a private intellectual outside of academia. And as I was tutoring, that brought me back around to math and physics. So I think I was just always meant to be a philosopher, basically, someone seeking fundamental truths. And by meant to be, I don't mean it was the universe's plan for me. It was my plan for me. I somehow made myself into that kind of person from an early age.
Interesting. Yeah. So I love the way that you go into proofs. I'm going to ask you about the scientific method in a moment, but whenever I first learned proofs, it was in geometry class. And I would sit there and look at the proof and not understand it. And I think it's this weird thing that we have been taught in society that you're either good at math or you're not, or you're good at science or you're not. Like it's something that not everybody can completely understand. And the way that I now understand proofs and now understand the scientific method, it's not something that is just entirely conceptual and you can't understand it unless you have a certain type of mind. It's kind of like a step-by-step process. It's this happens first, then this happens, then this happens. That is the kind of thing of proofs. It's like a hierarchical, you put things on top of each other. And that's what science is. It's like I have information and then I put more information on top of it. And that's really, really interesting to me. Can you explain, well, first, do you have any comments on that?
So I think I'm hearing some things I would disagree with.
Okay.
I don't know if I disagree. Here's the way, it's not really a disagree. Here's just the way I put it. You don't really see it out there that you're either good at math or bad at math, good at science or bad at science. There are a lot of voices out there that are really trying to encourage everyone to participate in math and science. The problem is that they don't realize why people feel the way you just, everyone feel, or not everyone, but especially the people who think they're bad at it, they feel the way you do about it. It's not that they're being told you're either good or bad. Maybe a couple people say that. It's that you go into the class and you feel like it. You just say, I'm just not getting this. And there's certain people for whom this just is straightforward. They're just crushing it. They're going right through the facts. And I think what causes this, the cause of this feeling is that math and science, that math is a set of process. I mean, we're talking about physics, but a lot of my work is actually in the philosophy of mathematics, or rather specifically in the inductions of mathematics. I also do inductions of math in order to start the inductions of physics. But anyway, here's the math is taught as though it's a system of procedures that you basically just have to memorize and plow through. And there's some people who are really good at basically just developing an intuition for an interconnected series of abstractions, basically. And those are the quote unquote math people. And I was never like this because I always refused to ever really commit something to memory until I knew it was true. And I was smart enough to brag a little bit. I was smart enough to understand why all the math was true up until about algebra 2. That's where I started slipping. So like, if you ask me how do you know, like, here's an example. When I was in 7th grade, you know how when you divide one fraction by another, you're supposed to flip the fraction and multiply?
Mm-hmm.
Like, that's a certain method. If I would have been able to tell you why that worked, how I knew that actually achieved division, I wasn't taking that on faith. And I can tell you, as a math tutor, everyone takes that on faith. Like,
I did.
The vast majority, yeah, right. Like, everyone's just like, okay, well, I guess I'm supposed to flip the damn number and multiply. Fine, I'll do it. So So you're taught that math is a procedure, and you're taught that science is a list of facts that you just got to memorize, basically. And there's some people who have a little librarian or a little computer inside their I mean, I'm being silly, but like their brains are just better at just memorizing huge volumes of facts. And there's people who are just better at going through a procedure. And those people excel in math and science. But of course, that's not what math really involves. That's not what science really involves. Math is a science. Math and science are observing reality and coming to conclusions about it. And that is a skill that can be learned. It's not something you're just naturally good at or bad at. Although there might be certain, more gifted and less gifted, but it's something everyone can learn. And a lot of things get in the way when it's taught to us as a procedure or just reams and reams of facts that we're supposed to accept.
Yeah, I love how you put all of that. So let's get into this. Let's first explain the difference between induction and deduction, because I think that that's a big topic that most people don't understand.
Right. So yeah, that's an important thing to start out with. So let's start with deduction. Deduction is where you have a set of facts that you already accept to be facts, and you make reasoning steps with those facts to arrive at further facts. So what would be an example? A simple example. So you let's say you know that the law of gravity is true. You know that a planet is moving at a certain speed. You know Newton's laws. You know how forces lead to changes in motion. You take these facts and you reason from them. You do some math. That's the reasoning from the facts. And then you do a conclusion. The planet is going to move in this kind of orbit. And maybe you write a mathematical equation that tells us where the planet will be at different times. So what you've done is you've taken some information, some facts about the planet, some facts about the way things move, some facts about gravity, and you've reasoned your way to the way the planet will move in the future. That's deduction.
Mm-hmm. Would another example be? I just want to throw out a kind of like an everyday scenario. Would another example be something like, okay, I know that I have 5 red pens in my purse. I pulled out 2 pens and they're red. I can deduce that the third pen is going to be red. Is that another example?
Yes.
Okay.
Yes, absolutely. Yeah. So like you have like the pattern here in all deduction is you have a certain set of facts that you take to be true, and then you identify more facts with those facts.
Okay. And then
Now, yeah.
you go into it, and then I guess we can talk about the problems with it.
Yes. So now induction is, how do you identify the facts to begin with? And the answer is you have to observe them. You have to observe the facts in order to identify them. Then once you've identified some facts, you can then make deductions to identify further facts. Now, here's the deal. Now, here's sort of the context where my work comes in. The laws of deduction were understood over 2,000 years ago by Aristotle. Aristotle identified certain laws of logic, and basically, that was basically it. People made a couple of clarifications and they systematized it, but deduction, the problem of deduction was solved long, long ago. So as a result, we have deduction completely on lock. Whereas induction, how do you, like, what is the rigorous method of proving a conclusion from observation? We don't have a rigorous method of doing that. And I'll give one example of the kind of thing this leads to is you'll see someone like Ben Shapiro say, everyone has faith. I have faith in God, he says. You have faith in certain scientific axioms. Why does he say this? He says, well, scientists are just deducing from a certain set of scientific axioms. I'm just deducing from the nature of God. None of us has a proof of our axioms, though. And I call BS on that. Like, we do have a proof of our axioms. You can identify the things you're deducing from, and then you can see that those things are provable from observation. The problem is we don't yet have a definite way of saying, I saw this, I went through these set of steps, and now I know with certainty that this statement is correct. I know, like, how is it, for example, that Newton was able to look at the stars and planets, not the stars and planets, the sun, the moon, and the planets. He looked at the sun, the moon, and the planets. He looked at falling objects and then did some reasoning steps somehow, and then arrived at the conclusion that gravity exists, that all mass attracts all other mass. He somehow gained certainty on that conclusion by reasoning from observation. So what is the right way of doing that? How do we know with certainty that's right? Do we even know with certainty that it's right? So that's the issue of induction.
So applying that to the last example, right? Would a problem be, for example, okay, I took out 2 pens of my purse. I know with quotation marks that there are 3 red pens, and it's possible that my knowing is wrong. It's possible that the information that led me to know is faulty, which would mean the 3rd pen is maybe blue. Then I would have deduced the wrong thing, and induction would not have taken it in that way. Correct? Reasoned in that way. In induction reasons differently than deduction. So then it would not have been.
Yes.
Okay.
Yeah, in this case, the inductive evidence you're using is really just observations of the pens. Now, induction specifically talks about general propositions, not specific ones. So in the case of your pens, you can just literally see this specific set of pens and see certain facts about them. Now, there are people who are skeptical about the evidence of the senses. I know Steve Patterson at least used to be skeptical of the evidence of the senses. I don't want to speak for Steve Patterson, but he used to at least be skeptical of the evidence of the senses. That's not where my work is. I take sense evidence for granted. I think there's I straightforwardly agree with the argument Leonard Peikoff gives in his book on objectivism. That's Objectivism, the Philosophy of Ayn Rand. In that book, he gives an argument for why the senses are valid. So I'm not going
What
there.
is the argument?
The argument is, so the argument, one argument, there's a few aspects that come together, but to do this as quickly as possible, all the information that you have comes from the senses. So as a result, and that includes The information led you to the concept of doubt itself. Like, why do you even have the concept of doubt? Well, you have the concept of doubt because you saw some stuff, you made a conclusion about it, then later you saw some more that made you realize you're wrong. And so when you have doubt as a little kid or whatever, you're basically saying, what if that happened again? What if I'm wrong again? What if I interpreted the facts wrongly? So even the very concept of that relies. So doubting the senses makes no sense. You can doubt a particular conclusion you reach on the basis of the sense evidence, but the sense evidence itself cannot be wrong. It can't, there is no questioning it, because you have to use the evidence of this in order to question it. So it doesn't even, it's incoherent to question the evidence of the senses.
Okay, that makes sense. And then how would you measure your sense? Well, I guess this goes into the scientific method, but I'll ask it anyways, and then you can divert as you would like. How would you measure your senses against reality? Like, hypothetically, you have a neural condition, or like schizophrenia, for example. There are ways that your sense perceptions are incorrect. How do you measure those against reality?
So yeah, so in other words, what about hallucinations? Is that what I'm getting?
Sure. Hallucinations, different, yeah.
So one thing worth noting is the way you're even able to identify a hallucination is that the experience of a hallucination is different from the experience from other experiences. One way or another, you find out that this wasn't real sense evidence. So, maybe you're having a hallucination of, a visual hallucination that when you reach out, your hand passes straight through it. Okay, this is something different. And so through a series of inferences, you might be able to see that your mind was creating this somehow. I haven't thought about this that much, but that's the kind of thing, that that's the kind of basis on which we reject skeptical arguments against hallucination. The onus is on the skeptic to show that the particular sense evidence you're presenting is a hallucination. If he can't just say, what if you were hallucinating? That's arbitrary. It's he who has to actually show evidence that you may have been hallucinating, or you may have used your senses wrongly somehow, or something like that. Until then, and by the way, this allows us to reject the argument from the Matrix. What if it's all a dream? Okay, well, what's your evidence that it's all a dream? The only basis on which we can accept any kind of argument is the basis of the senses, because that's all we get evidence from. And if you're in the Matrix, you end up seeing evidence. I mean, this is a little silly to even entertain it, but like, if you think about the movie, like he sees evidence, like things aren't quite right to him. He can see like things change, and things just suddenly change, and he knows reality can't work by magic, except he's in a simulation. So the machines can make, they can make walls appear whenever they want. So you can see that something is different from the way it's not a reality. It's a reality, which is, it's a simulation created by someone else. And there's actual evidence of this that he can point to. And that evidence is how he ends up getting out. And until such evidence is given, it's a non-scientific claim. It should be, as Newton said, and Newton understood this actually, said, any claims that don't have evidence should be dismissed without contemplation. You don't even have to give arguments against them, because in fact, no argument was given for it to begin with. It was a what if, but there's an infinite number of what ifs. What if, there's aliens and they're, manipulating your brain? What if there's a teapot flying around the earth right now? That's a common one that's brought up. There's an infinite number of things you could think of and say, well, what if that? Like, hey, and I'm going to pretend that that's true until you disprove that there's a teapot flying around the earth. So that's the basis on which we, I dismiss skeptic arguments against the senses on the basis of dreams or hallucination.
Okay, that makes sense. And then you draw a line between, just for clarification's sake, you draw a hard line between senses, as in I see something, hear something, feel something, etc., and feelings. I feel something.
Yeah. Yes. So yeah, emotions.
Mm-hmm.
So our perceptions are the data that we're actually getting from reality. Our emotions are our body's automatic responses to our values.
Mm-hmm.
So if you have a friend and your friend is being treated poorly, you get angry. Like, my friend deserves better than this, and I'm going to change the situation. I'm going to, get mad at I'm going to get mad at the waiter on his behalf and make sure he gets the food like that he asked for, and he's not standing up for himself, maybe. But here's the so your emotions are a response to your values. And here's the thing: you pick your values, and you could have picked them wrongly.
Mm-hmm.
Your emotions and also in any given instant, not all of your emotions that you have in any given instant may not reflect the full set of facts. So, for example, when I was in grad school, or when I was in physics class, when I ran into trouble with a problem, I had a strong desire to complete the problem at all costs, even if it took the next 3 goddamn hours. Sorry if we're not supposed to say that, but that's the kind of swearing and stuff. That was the kind of commitment I had. If it takes me the next 3 goddamn hours, I'm willing to do that for this problem. And part of what was going on is I was afraid that I wasn't good enough to be a physicist. So what was happening there is feelings were causing me to focus on certain goals instead of seeing the bigger picture. What's my bigger picture goal? My bigger picture goal is to learn physics and to pass this class. Is doing 3 hours on one problem really going to help me with that? No. So our feeling is, so looking at the full context is looking at the full set of facts that need to inform our decisions. That's what's really important. And our emotions on their own don't allow us to do that.
Okay.
But emotions are important because they give us information about our values. So they are important, but we shouldn't make decisions based only on our emotions.
And I wanted to expand on that a little bit, because whenever it comes to interpreting observations, a lot of the time we take in our perceptions, and we take in our perceptions as we understood them. Like we impose the why on the observations as well as the what. And whenever it comes to the scientific method, as we will get into it, and making observations, it's more about the what. And afterwards, then you start talking about the whys, correct?
So the what is what you're seeing, and then the why is the underlying facts which are causing the phenomena you're seeing. Is that what you mean?
Well, I think the why could be open to interpretation, depending on what. There are some whys that are facts, and there are some whys that are not facts, like the waiter being rude to you. That is not necessarily a fact, and it's not, you can draw conclusions about him as a person, etc. But whenever you are trying to evaluate the situation and make observations, that shouldn't come into your purview.
Yeah. So the way I would put this issue, tell me if this addresses what you're trying to go for. We need to make a distinction between perceptions and inference from perception. So
yes, I would agree with that.
If if you're able to make that distinction, then you are able to be objective. You're able to look. It is possible to, it's hard, but it's possible to actually look at literally what you perceived and understand that that's what you perceived, and not bring and only bring inferences in which are validly justified. Again, it's hard, but with the right method, it's possible. And especially in the course of science, when you have months to recheck over and over again, to revisit the issue, to make sure you are taking everything into account, etc., then it's very possible. And this is how we ended up landing men on the moon. This is how we're able to land men on the moon, but occasionally we might snap at the waiter because we didn't, understand the full situation. like both of those things are possible to humanity, because if you apply a rigorous method over the course of time, it is possible to actually come to understand the facts. But let me clarify this a little bit more. So there's a difference. So I disagree with the idea that you have no choice but to bring in biases to your interpretation of observation. So psychologists will, for example, give studies. Well, they'll do studies and they'll say like, oh, well, 99% of witness testimony is false, or whatever the number is, it doesn't matter. Because of course, a lot of witness testimony is false, because being objective and not bringing your own facts to the table, or bringing your own biases to the table, and reading into and changing the way you remember what you perceived, doing that or not doing that is really hard. It takes a lot of effort that most people don't try to exert. To do that, to just say, okay, what were just literally the facts? What were the literal perceptions that led me to this? You need to be able to do that. And then now you still need to make inferences. You need to bring your prior experience to what it is you perceive. But you need to make sure that you're making proper inferences from the facts.
Do you think
from what you perceived?
Do you think it has to do with the fact that we like stories as humans? So it's easier for us to remember things as a story. So, for example, the person that's on the witness stand, like they remember something as it is because they remember it sequentially as a story, not as the observations that occurred. Like understanding something in terms of observation, I have to try really hard to observe everything or individual pieces of something.
Yeah. The way I understand this is that it's really hard to remember a bunch of unrelated facts.
Okay. Yeah.
Because there's just your brain literally gets overwhelmed. There's just a bunch of facts. And so one way that helps you remember it is to impose some kind of common cause over it. So if you have a narrative, as you're putting it, or as I would put it, like if you have some hypothesis about what the underlying cause was, the waiter did this, the waiter got my order wrong. The waiter, didn't take very much time to discuss the menu with me. The waiter looked at me that certain way. The waiter did all of these things because he doesn't respect me. So like all of these separate facts, it's easier to remember them all if there's some kind of common cause that you attribute to it. But that of course doesn't mean that the common cause you're attributing, that's not evidence that that's the cause. It's not conclusive evidence that that's the cause. So this is one of those things that gives rise to common biases. Is it's easier to remember something when you can tie it all to a certain conclusion. And that's one of the things that makes it tempting to jump to conclusions. It just makes things easier.
That makes a lot of sense. Okay, let's jump into scientific method. As a college professor, I imagine that you've given this spiel a couple of times. So I'm just going to entirely let you have the floor right now. What is the scientific method? Why do we need it? Explain it to us in the way that we needed to be explained it in the first place.
Okay, so let's see. I'm not sure if I could have explained this to you when you needed it back in high school or junior high, but I can explain it to you now and to your audience's level. So we need a scientific method because our survival depends on identifying the facts. We need and so I treat a scientific method as an inductive method, a method of reasoning from observation. We need to identify the facts if we're going to live. If we don't identify the facts, or if worse, if we think certain things are facts that aren't, we end up making bad decisions, and that leads to suffering and death. So that's the ultimate reason we need it. And the other reason is that not just any method will end up getting you the truth. There are some methods that won't get you the truth. But here's the good news. there is a method that you can, that based on your understanding of the method, you know that if you stick to that method, you will arrive at the truth. It doesn't guarantee you that you will arrive at all truth, but it guarantees you that whatever truths you do end up discovering, you can be certain of them. That's what a correct scientific method would achieve. And so what do I take to be the correct scientific method? So long story short, I'm writing a whole paper on this, which I'm hoping will be done in December, or at basically the end of the year, end of 2022. But I'll start by differentiating my view from the view you probably learned. So the view you probably learned probably goes like this. You do some research, you have some background knowledge, they say. That's right, that part is fine. Then you make a hypothesis about some particular phenomena. So there's some particular phenomena out there. Let's say, all mass attracts all other mass. It's Newton's theory of gravitation. That's your hypothesis, okay? You see the planets moving in the sky. You see the moon moving in the sky. You see objects fall and you say, okay, the cause of all of this is the fact that mass attracts other mass. That's the underlying cause of these things, of falling and of planetary motion. Okay, so you have a hypothesis. Then what you do is you conduct an experiment. You conduct some kind of experiment. Then what you find is that in that experiment, your hypothesis is either able to make a correct prediction or an incorrect prediction when you make that experiment. New discoveries have to be consistent with what has been discovered and proven already. So here's an example of this. A key aspect of my theory of induction is that any one conclusion relies for its proof on earlier conclusions. So, for example, when you wiggle a string, you're able to see that there's a wave. Okay, when you wiggle a string, there's a wave on the string. Okay, and when you ask yourself, why is it moving that way? You're able to combine your understanding of really basic kindergarten physics with an understanding of why the wave is moving. You're able to understand why the wave is moving that way using a basic understanding of physics, which is, okay, like I'm moving this piece of the rope here with my hand, and then the next door neighbor piece of rope is getting pulled up by that, and that's pulling up the neighboring rope, and that's pulling up the next neighboring rope, and that's pulling up the next neighboring rope. And then after a while, it can't move any further up, so it starts going down. And then that pulls down the neighboring rope. So if you look at it closely enough, you can see why the wave is doing this. And you can see that it has humps. And you can see that a hump that goes upward, if it overlaps with a hump that goes downward, it creates no hump at all. If these two, this is called destructive interference. Now,
Interesting.
Yeah, so you, let's say you have that. You have some understanding of waves in your repertoire. Then later you see some evidence that light is a wave. You see that the evidence that was indicated that light was a wave was that when light passes from one material to another, it bends. And it turns out that waves also do this. And so one reasonable hypothesis was that light is a wave. And the way that this was confirmed was by having two sources of light overlap with one another. It was found that when two sources of light overlap with one another, when they hit a screen, some parts of the screen were bright and some parts of the screen were dark. And that is a property of two overlapping waves. Because like I said, when you have two waves overlapping with one another, the up humps and the down humps cancel. And they were able to see that light, when it overlaps with itself, also has this property. So that which has the properties of a wave is a wave. And that is a way that that's another method of scientific proof. You say that which has the properties of something is that thing. It's a wave. How do I know? Well, it has the properties of a wave. Because what else would you call it? So now you're able to see that light is a wave because it has the properties of a wave. And that's the kind of reasoning which actually allows us to gain certainty. So it's true, the guy who did this experiment, he was probably predicting that he would get the light and the dark fringes, the light and the dark, things on the screen. Yeah, sure, he made a prediction, but that's not the important part. The important part is that interference, having the light parts and the dark parts, that is a property of waves. And that which has the properties of something, it is that kind of thing. So this is the and this requires reasoning from earlier scientific conclusions. You can't do this unless you already know exactly what a wave is and why it has those properties. If you don't have that earlier knowledge, then you're not able to make scientific conclusions like this from certainty, with certainty.
And that's why you're very adamant about going back to the beginning. Like, even in anything, pretty much. Like, think about your own values, for example. I like to apply things to many different things, but for example, if you are trying to reason from a place and you have a certain value system, but something's wrong or not in line with truth or whatever, at some point you'll get a mismatch. And that's just one application of it, but it can be applied to many, many different directions. And that is why you were so adamant about that.
Yeah. So I mean, in the case of in my case, what I'm doing with my theory of induction is I am trying to re-systematize physics. I'm trying to go back to the beginning and start over. And the reason I'm doing this is because there's a lot of evidence. I mean, there's, in my view, conclusive evidence that quantum mechanics and relativity are flawed theories. And I can tell you more about that, but for your listeners, if you want, like, my understanding of why they're flawed theories, look at the work of David Harriman. He's an objectivist physicist, or was an objectivist physicist. And he, and I straightforwardly agree with what he says against those theories. For example, really quick, particle can't be a wave and a particle at the same time. That's just a contradiction. And there's other things that make me think that there's a lot of other reasons I think that these are flawed theories. And so having a theory of induction gives me a unique opportunity to actually start over. So what I'm doing is by starting from the beginning, by starting from ancient Greek astronomy, basically, and going through the observations and the reasoning steps, which did allow the Greeks to know that, for example, the Earth is a sphere. The Greeks figured out the Earth was a sphere without ever going to space. They inferred it from the shadows that the Earth cast on the moon. They made all these inferences, which led to Copernicus's understanding that the Earth is going around the sun, and then that led to Newton's theory of gravity. And then that also led to Newton's theory of the laws of motion. And then other investigations in chemistry allowed us to understand that matter is made of atoms. Then an understanding of Newton's laws of motion and the fact that matter is made of atoms, that allowed us to understand that heat is actually a form of motion. Then that was combined with an understanding of electricity and magnetism and such. And I've actually gone through, and there's a lot more to that story, but I've gone through much of this story and actually proved it, actually showed how each observation led to each conclusion, then how each conclusion inspired further observations, and how those conclusions, in combination with those further observations, allowed scientists to make even further progress, and so on and so on. It's this constantly building process. And this allows me to actually see the proof for these ideas. And and so the goal is that by the time I actually reach the evidence and actually reach the position where I'm ready to read the evidence for quantum mechanics and relativity, which I haven't gotten to this yet, but I'm close. Once I actually look at the evidence that led to the theories of quantum mechanics and relativity, I will be in a unique position, like an unprecedented position in history, to actually look at these observations with fresh eyes, without bringing interpretations that I learned in school to these facts and just look at the facts themselves and reinterpret them. And that means a better theory of quantum mechanics and a better theory of relativity.
That's so interesting to me. I have a question about kind of how you went about creating this curriculum for yourself. Like, how did you backtrack everything? How did you say, okay, this is where I need to begin?
That's a good question. The way, so like the first answer is just a lot of work. It's actually really, really hard because you have to use your knowledge that you learned in school while also only using it once you actually reproduce the proof of it. And what that means is you have to be really careful what order you go in, because a lot of times you'll find yourself reasoning with certain facts that you haven't yet established in the narrative. Another part of the answer is that I had a lot of help from David Harriman. David Harriman already has a class where he does this. What he does is he basically goes through the history of science, but he's not careful to make sure that each stage is really proven. He has a sense of what science, like he has a sense of what it means to only move on once he's proven something, but he isn't trying to rigorously stick to that. But even though that's the case, it just helped me a lot. So someone has already tread this ground. So that helped a lot. But then how did I know where to start, you ask? Well, I started with basically a caveman context. Although I've only made my videos start with the ancient Greeks looking at astronomy, but my inductions that I've written on my own actually start with a caveman learning to count. So like imagine someone who they know how to cut meat with knives. They know how to talk. They know how to fight. They know how to build a hut. So you have this basic knowledge that is accumulated over the course of a caveman's life. But he doesn't have any scientific knowledge. So for example, he doesn't have concepts of number. So assuming he had some basic understandings, how would he come to a concept of number? How would he discover that? And the way I say it in my story is I kind of have a dramatic story where there's the chieftain of a tribe and he's looking at his army and he's looking at an enemy army and he says, wow, well, I don't know who has the advantage. I don't know which side has more men. They have a larger camp, but our camp is denser, like all the men are packed in more. So I don't know who has more men. Then he realizes, wait a second, if I put a rock into this bag for each of the men I see in the other camp, I can bring it back to my camp, hand each of my men a rock, and if there's leftover rocks in the bag, I know that they have more men. But if not all of my men end up with a rock, I know that we have more men. And so this is a story which teaches us how someone might have discovered a basic quantitative method, a basic mathematical method of pairing things off to see which group has the larger quantity of things. So, and so that's where I start. I really start from the beginning, and get through math that way. And then that forms the foundation for physics.
Definitely dramatic. I like it though. It's really interesting to me how your theory of the scientific method, I mean, not even your theory, but to think about the scientific method as in, okay, for people to have decided to come to a conclusion, they needed to need it. Like for somebody to, start thinking about numbers, there needed to be a reason. For a long time, you could get away with, oh, they're just a group of sticks. I don't need to know how many sticks there are. But at a certain point, you do need to know how many sticks there are. And at that point, that's whenever it actually becomes necessary to count. That's crazy. Like, it's so simple, but it's
Yeah.
almost like, wow.
Yeah. And yeah, what you're touching on is a huge aspect of my theory of induction, which is motivation. I believe that that part. So the way I put it is this: is not only does science not arise until there's a need for it, but that need is actually part of the prior knowledge required to come to the conclusion. And here's why that is because, first of all, you need to, in science, part of the scientific method, which isn't in the modern scientific method, is that you need to justify your question. You need to justify why this question is worth asking. A lot of times in science, and I bet a lot of your audience, if they're in academia, will be able to relate to this. A lot of times the reason a question is being asked is, I need to publish. Number one, I need to publish. And number two, no one has asked this question before. Well, wait a second. Is this question going to give us knowledge that actually improves the human condition? Well, we're just doing science here. We're just exploring. Like, yeah, but do you have any reason to think that exploring in this direction will actually yield some kind of helpful result? That onus is on the scientist. Yeah. In addition, the reason you're investigating something actually influences the way you end up formulating the knowledge. So, for example, why is it that we moved from Roman numerals to base 10 to the numbers we have now? Why didn't we just stick with Roman numerals? Well, because the numbers we have now, they represent the same quantities, but they're more efficient at identifying those quantities. Why do we have exponential notation? When you do 10, 2.3 times 10 to the 12th, like, why do that? Well, because some numbers are so enormous that you're willing to sacrifice a little bit of precision to just quickly get out like what the size of the number is. It's roughly 10 to the 12th power is what you're trying to say. So our reason for conceptualizing knowledge actually has an effect on the way we conceptualize it. And if you don't include that reason, that motivation, then a lot of scientific concepts become really hard to understand. Yeah, it becomes watered down. It comes off as arbitrary. Like, if you're ever in math class and you said, like, what the hell does this mean? Like, what the hell is this even referring to? Or like, why? Here's a better way of asking it. Like, why do we need this? And by we, you're not saying, why do I need this? Why am I? Because a proper perspective in colleges is, hey, I'm going to learn a lot of things and just sort of learn how to think. But the right question is, why would anyone need this? Maybe I won't need this for my job, whatever, that's fine. But why would anyone need this? Like, what was the need that gave rise to this? If you don't have the answer to that question, then you won't understand why the knowledge is formulated in the particular way that it is. So
that's interesting.
So that's another aspect of the theory, is that our values are part of the scientific method. If they're part of the way you reason.
This actually makes a lot of sense because, well, whenever you look at history, there are certain times, especially times of great problems, in which we have massive scientific breakthroughs. And I think it might be because we start deliberating better. The questions that we ask become better because we actually have a reason to ask them. Like, the stakes become higher. Asking questions, doing experiments, there are higher stakes to those things. So then people are asking better questions and doing better experiments and getting to actual conclusions. Like, it's interesting, I hadn't thought about this, but there are a lot of cases in which we ask questions that, like, if you ask, why are we asking them? Usually there isn't a good answer to that.
What would be an example of what you're talking about here?
I mean, you can use the teapot example. Like, oh, is there a teapot spinning around the earth? Like, maybe. think that maybe it's the idea of the wow factor almost. Like finding something in science that nobody had thought to ask before, or finding something that nobody thought to look into before. And maybe it turns out to be true. And like, I think that could be an interesting motivation for asking a question like the teapot question, you know, or really, really diving into the matrix question. Like, are we actually living in a matrix? I mean, maybe, but like, why do we ask this?
Right. So, okay, I see. Here's an example. Here's an example of like a question and a theory that makes no sense until you understand why the question is being asked. So the way before it was proven, the ancient Greeks thought that everything was made out of atoms. So like, you know, people are made out of lots of little small particles. Rocks are made out of lots of little small particles. So like, why did they think? So you could say that, so, you know, they can tell you that, like, I think everything's made out of small particles. And you could say, oh, wow, gee whiz, like, that's really cool to think about. But like, well, what the hell does that even mean? Like, how small are they? Like, and how can we even use this information?
Why does this matter? Why do I need to care?
Why does this matter? Yeah, like none, you don't, this is basically useless information until you understand what kind of question it actually answers. And what was the question it answered? The Greeks were having trouble understanding how change was possible. That's what led to the theory of atoms, is they were thinking about, they were trying to understand why certain things changed into other things. Because they were trying to ask that, you know, so like, why is it that wood turns into ash as it burns? Why is it that grape juice turns into wine as it's left out? Why does change, like, what causes these changes? And why do we want to know about these changes? Well, so that we can cause these changes. Like, what's at the heart of change, so that we can not just turn grape juice into wine by leaving it out, not just burn wood, but actually get to the fundamentals of what causes change. And this is basically chemistry, right? And in the modern day, we've answered a lot of these questions, and we actually can change chemicals to a great degree to make life-saving medicines and different fuels and different materials and all kinds of amazing things. So, you know, computer chips are made of a completely artificial material you'd never just find lying around. You know, they're a processed material. So we needed chemistry to understand how to do that. So the Greeks were trying to understand these sorts of issues, but as they came across it, they said, wait a second, we don't even understand how change is possible to begin with. How can one thing, everything is what it is, so how can it just suddenly become something else? That actually defies logic. Like, logic tells us that everything has a certain identity, but how can something just go like, well, bam, and now it's just a different identity? And one proposal for this is that all things are made out of lots of small parts or atoms, and the atoms don't change. The atoms aren't just magically poof changing into something else, but the atoms are rearranging themselves in certain ways. And that's what gives rise to the changes that we see on the macroscopic level. So the Greek theory of atoms was actually a hypothesis to explain why change even occurs to begin with. It's that it's not that something's just poof changing into something else, like the material is changing, but it's actually just the parts that are changing their relationships with respect to one another, and that gives rise to the change.
So how do you track back the history of questions? Like, how do you find the questions that people were asking in that time?
I don't find them. I make them up, actually. Although sometimes I find them in the historical record, but a lot of times what I do is I make them up. My inductive proofs are a fictional story. They're based on the history, but here's what I do is I say, given that scientists knew this thing, that thing, this thing, that thing, what would they have been motivated to explore next? What would they have had the power to discover next based on what they knew at this stage of the story? That's how I do it. At every stage, I think about what kinds of observations they could make and which observations they would be motivated to make based on what they know at that stage. So here's an example. The lunar eclipse happens every once in a while. The moon suddenly becomes dark. Okay. Now, the Greeks would, early stargazers would not have been able to notice this irregular darkening of the moon unless they first understood the regular phases of the moon. The moon becomes a crescent, and then like a fatter moon, then a half moon, then a gibbous, then a full moon, etc. It goes through these phases every 28 days. So in my narratives, the astronomers have to understand that 28-day cycle before they discover the lunar eclipse, before they're able to even notice, oh, hey, the moon suddenly got dark out of schedule. This must be a new effect. This must be some new thing. So a discovery like that is only, and that kind of observation and that kind of question is only possible once you even understand the regular cycles of the moon. So your knowledge, this is one way in which knowledge always opens up later knowledge or further knowledge.
Interesting. Does it ever cross your mind that, like, where do you think your blind spots could be? So, like, I am thinking about this in terms of something like medicine, for example. Like, I was thinking about ways to learn medicine so that I both really understood it, like actually understood it, and that I understood where we came from. So, like, both I understand the science and then I also understand the reasoning, and I understand the questions that people were asking to get there. But this idea of looking at history and looking at physics at the same time, I mean, in some senses, you are a true philosopher, because philosophers care about questions. So then and wisdom. So then it's like you've put together a lot of complementary parts: history, the physics, just regular logic, like understanding things, geography, etc. Like, how do you know that you are doing this correctly? Or like, why do you trust yourself and your conclusions?
The reason I trust myself and my conclusions is because I've written a certain story, and as you're probably noticing, like, okay, if it's just a story, then how do you know that the story is correct? Like, how do you know? And here's how you could know is you could know by saying, okay, if I were to actually conduct these observations that I've written out in the story, would you actually see the things? Would you actually make these observations? Would you actually see the things I'm claiming you'd see? And what's happened is it's like I'm putting together the observations that were made historically. I'm just putting together those observations in a different order, because historical order is good because it's actually an order of proof. It's just kind of a complicated order of proof because people took a lot of wrong turns and inefficient routes the time, and I want to present that proof efficiently, not historically. So all I'm doing is taking the observations that other scientists have already made and simply reordering them so that one can actually go through the reasoning steps to reach each conclusion separately. That being said, there are some of my experiments and observations that were not historically conducted, and these need to be reconducted. These observations will need to be conducted over again, and I might reconduct them over again, depending on if I think they really need to be conducted over again, or I will simply leave that to other thinkers, because basically this whole process is already going to take several lifetimes worth of work. So I probably won't be reconducting that, because I think getting to the end, even if somewhat imperfectly, getting to the observations and reasoning steps that give rise to quantum and relativity, if I get to that stage, even with a basic inductive narrative, maybe with a few flaws here or there, that will still be an unprecedented position from which to try and understand the observations that gave rise to quantum and relativity. That being said, I am taking a risk in doing this. Because I may miss something. By not conducting the observations myself, it's totally possible I miss something. That's just a risk I'm taking. But it's a risk I might not have to take if it's a risk I may not have to take if I get the right collaborators. And I already have a few people who are helping me with the inductive physics project, including one physics professor at the University of Wisconsin, or I'm sorry, the University of Madison, who is conducting a class based on my inductive physics lectures.
That's
and
cool.
So if the inductive physics project, if I get enough collaborators, I might have an experimentalist who goes out and checks some of these things that need checking.
That's really cool. Yeah, it's an interesting thing because, like, whenever I watched your first lecture and you went through the weather scenario where it was basically like you proposing this instance. I don't know if you want to do it right now, just so that we give context. It's very short.
Yeah. So this was the proof that the sun is the cause of the seasons.
Yeah.
So the proof. So one of the first astronomical integration I make in the inductive summary of physics is, you imagine an ancient Greek philosopher or astronomer, and he notices that the sun is out longer during the summer months, during the hot season, and it's not as long. The days are shorter during the winter. And so he says, okay, well, maybe I know that the sun heats things up, so maybe the hotter weather is caused by the sun being out longer. And so what he does is he conducts an experiment to see if the hotter weather is correlated with the longer days. And he finds that the longest day actually and he finds that the hottest day is actually lags about 2 months behind the longest day. And so that is a little bit of a hiccup, but then he realizes that it actually takes objects a while to either heat up or cool down when they're brought near a heat source or removed from a heat source. And so he's able to conclude that the sun is indeed the cause, the sun being out longer is indeed the cause of the seasons.
Mm-hmm. It was interesting. So the point I was going to make, thank you for sharing that, was that I listened to that and it just made sense. Like, there are some things that you hear and you're like, oh.
Yeah, well, thank you. And that's great, because that's exactly what I'm going for. My goal, my vision is this, is that right now we have a society of people who follow the instructions of scientists. Basically, scientists find things out, and then people basically apply those principles towards some kind of productive end, whether it's medicine or engineering. But the people applying those principles don't generally understand them for themselves. They're basically following the instructions of scientists. Now, however, there is, and gaining firsthand knowledge basically takes a lifetime of experience, and only in your particular field.
Mm-hmm.
But what if all science was actually systematized in terms of the proof? What if you could open up a textbook and actually see the observations and reasoning steps, just like I gave with the seasons, the actual observations and reasoning steps, which allow you to see for yourself individually that particular scientific conclusion is true? That would change us from a race that is able to give birth to the occasional scientist into a race of scientists. So think of what we would be like if actual firsthand scientific understanding were just as common as literacy is today. That's my vision for what this system can make possible.
And I think that's amazing. I think that's necessary. It's not the feeling of being bad at science. Like, that's not how it is supposed to be. It's fact. You're supposed to be able to understand it, and it's supposed to be easy, and it's supposed to be kind of like, well, it's supposed to be sequential. It's not supposed to be faith. It's not supposed to be something that you learn and kind of understand, but mostly just apply. Like, you you can't build on that. And I think that's really, really interesting to me, is the idea of, okay, where do we go? Like, if people start thinking in terms of what has been built on in the past, the amount of things that we could build in the future are incredible.
And if we actually understood that knowledge of the past for ourselves instead of taking it on faith, that would also bring about much more innovation, because innovation is only possible when you understand the principles for yourself. And people are already innovating at an amazing rate, but they're only able to innovate in those based on the principles that they personally understand. And so much of the knowledge out there is not generally understood in terms of the actual observations and reasoning steps which prove it. But that is what this system will make possible. You can systematically understand the proof of scientific ideas. Yeah, so that's what I think. That's why I get out of bed in the morning, because it's a mission. I couldn't think of a better mission in life, to make science itself better.
Yeah, no, that's amazing. What do you see that looking like in terms of, so you mentioned that you are outside of academia. What do you see that looking like in terms of the way that we first do academia, and then second, like the actual practice of things? So engineering and medicine and, physicists practicing physics, like how would the practice of things change?
So one, I'm not sure about industry. As far as I can tell from industry, things things are going great in industry. I haven't worked that much in industry though, so I'm just not sure. Maybe I would have my own ideas there if I had worked in industry. But in terms of academia, which I was working in, there is a very anti-science mentality in academia. And that anti-science mentality is what I call science by consensus. And you see this in the news all the time. And you see this in the realm of global warming science and the science, the science that pertains to vaccines and health and issues related to COVID-19. Now, I'm not going to talk about the particular views I hold on those subjects, because that's not really important here on these subjects. Is man-made global warming real? Are the vaccines working? Stuff like this. Like, I'm not going to comment on these questions, but I'm going to comment on the method that is often relied on in order to try and convince people of answers to these questions. The method is that we're the experts. We have certain knowledge you don't. We're able to come to conclusions about this, and you can't come to conclusions about this. But I'll tell you, as someone who's in academia, when you actually talk to the experts that have these views, especially in physics, they also go with the consensus. The amount of things that they feel comfortable giving their own personal opinion on is very narrow. And the reason for this is that they don't have the firsthand experience required to make judgments on a lot of things. It's just on their narrow field. And as a result, they end up getting pulled along with science by consensus, even though they are the experts. They are themselves the experts. And so that's something I'm hoping to change, is that if the right scientific method were readily available, and that the achievements of the past could be actually understood in a first-handed way, then we'd be able to, then that would bring back the realization, the scientific ideology, that we have to that science means making up your own individual mind, regardless of the consensus. You might use the expertise of other people. You may use the information they have that you don't, but at the end of the day, you make up your own mind. And that kind of individualistic thinking is really rare in academia.
That's interesting.
Yeah.
Okay,
Yeah.
so We have time for one question. If you could leave only one piece of advice for the world and generations below you, what would it be?
Think for yourself. Everyone says it. Not a lot of people do it. Stick to that.
I love that. Okay, well, we will definitely have you on again, James. Thank you so much for sharing. I have loved this conversation. And I will definitely put all of your links below. Is there anywhere that people can find you if they want to find you?
Yes, the main place to find my work is on YouTube, and just type in my name, James Elias, and Elias has 2 L's. So just type that in, and you'll find my you'll find all my work there on my YouTube channel.
Perfect. Thank you for coming on, James.
Thanks, Ella.
I hope that you found this episode enriching. I would love to hear your thoughts. If you would like to write a rating or a review, that would be fantastic. You can also follow me at Induction Podcast. I'm looking forward to our next episode. Cheers.
We all want to help one another. Human beings are like that.